Welcome to this video. Good morning, good afternoon, good evening, based on the time you are watching this video. And in this video, we shall discuss chemical kinetics. Chemical kinetics. You shall know the meaning of chemical kinetics. What is the meaning of chemical kinetics? Chemical kinetics is a branch of physical chemistry that deals chemical kinetics is a branch of physical chemistry. It's a branch of physical chemistry that deals with one, rate of reaction, rate of reactions. It deals with factors affecting rate of reaction. Factors affecting rate of reaction. It deals with what? Mechanism of reaction. Mechanism of reaction. It deals with mechanism of reaction. These are what we are going to discuss under chemical kinetics. It's a branch of physical chemistry that deals with rate of reaction, factors affecting rate of reaction, mechanism of reaction. And before we know, this can be what? Can be widened. This scope can be widened. I can say under what we are going to discuss under chemical kinetics, we are going to look at rate of reaction, as I said, rate of reaction. We are going to look at rate of reaction. We are going to look at factors affecting the rate of reaction, affecting rate of reaction. Rate of reaction, I can write ROR, rate of reaction. Under factors affecting rate of reaction, we are going to look at discuss some factors that affect rate of reaction, like temperature. We have like temperature. Under temperature, we shall discuss Arrhenius equation that says rate constant equal to what? Pre-exponential factor times what? Times Euler's number raised to power what? E minus A, which is what? Activation energy over RT. Then we shall discuss under what? Factors affecting rate of reaction. We are going to look at concentration also. Concentration. Under the concentration, we shall discuss order of reaction. We shall what? First order of reaction. We shall look at second order of reaction. We shall look at third order of reaction. We shall look at pseudo order. We shall look at zero order of reaction. We shall look at this. Then, what are we going to look at again? We shall look at rate law. We shall discuss rate law. We shall discuss molecularity, and we shall discuss mechanism of reaction. We shall discuss mechanism of reaction. This is everything we are going to do under what? Chemical kinetics. Rate of reaction, factors affecting rate of reaction. Under factors affecting rate of reaction, we have 7 factors. I shall discuss 7 factors. They are under the factors. We shall look at these 2. They are very important. Temperature, how it affects. Under the temperature, we shall discuss what? Arrhenius what? Equation. Then under the concentration, we shall look at what? Order of what? Reaction. We shall look at what? Rate law. We shall look at what? Molecularity. Then we shall look at what? Mechanism of reaction. But in this video, we are going to look at three things rather. We shall going to discuss rate of reaction. We shall discuss factors affecting rate of reaction. We shall discuss rate law. These are the two things. Then this Arrhenius equation and order of reaction will be discussed about in the next video. Take note of that. This Arrhenius equation and what orders of reaction, first order, second order, third order, zeroth order, pseudo order. We shall discuss those in next video. But let us start. The first thing to start with is what? Rate of reaction. Let me write what we are doing today. What we are going to do today in this video. Let me write it. We shall look at, I said, let me write it here. Rate of reaction. ROR. We shall discuss factors affecting rate of reaction. Then we shall look at rate law. We shall look at rate law. Let us start with the first one. Rate of reaction. Rate of chemical reaction. Rate of reaction. What is rate of reaction? Rate of reaction. This is the change. This is the change in concentration. Concentration of reactant or product per unit time. This is the change in concentration of reactant or product per unit time. Don't forget, whenever you see rate, it means speed. The speed at which the reactants are consumed, or the speed at which the products are formed. The speed at which the reactants are consumed, or the speed at which the product are formed. That is rate of reaction. This is the change in concentration of reactants or products per unit time. That is the speed of a reaction. That is what? Rate of reaction. The speed of a reaction. Take note of that. Since we know that the rate of a reaction is the speed of a reaction, change in concentration of reactant or product per unit time, I can say rate of reaction equal to change in concentration. Change in concentration over change in what? Time. Change in concentration over change in time. From here, we can get the unit of what? Rate of reaction. What will be the rate of reaction? The unit of rate of reaction. Don't forget, concentration is measured in what? Mole per liter. Mole per liter. While time is what? Measured in what? Seconds. Therefore, the unit of rate of reaction is given in what? Mole per liter per what? Seconds. Take note, this is the unit of what? Rate of reaction. The unit of rate of reaction is what? Mole per liter per seconds. Take note of that. Then before we move further, we shall discuss these reactions. Under rate of reaction, we have a particular reaction that we can measure its rate. It's not all reactions that the rate can be measured. There are some particular reactions that the rate can never be what? Measured. And there's a particular reaction that the rate can be measured. Look at this. When you have this, look at this. we have three types of reaction based on rate of reaction. We have very fast reaction, very fast reaction. A reaction that is very fast, the rate of reaction cannot be what? Measured. An example of very fast reaction, we have ionic reaction. Ionic reaction. Ionic reaction. What do we mean by ionic reaction? For example, when we have silver triazonitrate 5 reacting with sodium chloride to give silver chloride plus sodium triazonitrate 5. In this case, this is an ionic reaction which can occur in microseconds. It's very fast. We cannot measure the rate of this reaction. A very fast reaction, the rate of a very fast reaction cannot be what? Measured. Look at this. This is silver ion, nitrate ion, plus sodium ion, chloride ion. It's an ionic reaction. It is very fast. The rate of reaction cannot be what? Determined, because it can happen within what? Microseconds. It is very fast. We can't measure this. Then another reaction, we have very slow reaction. Very slow reaction. Very slow. Very slow reaction. Slow reaction. An example of this is what? Rusting. Rusting of iron. Rusting of iron can take years. Can take what? A year, 2 years, can even take what? Months for it to occur. It is a very slow reaction. This one can never be what? Determined. The rate of reaction of this can never be what? Determined. A very fast reaction, which is ionic reaction, and a very slow reaction, such as what? Rusting of iron, its rate of what? Reaction cannot be what? Determined. Let's just look at this moderate reaction, where you have moderate reaction. A moderate reaction, the rate of chemical reaction of a moderate reaction can be what? Determined. That is, this one is what we determine on the rate of reaction. A moderate reaction. We determine the what? The rate of reaction for what? Moderate reaction. Moderate reaction. Example of moderate reaction. When you have decomposition of hydrogen peroxide to give H2O plus what? Oxygen. It's a moderate what? Reaction. It's a moderate reaction. This one, the what? Rate of reaction can be determined. For example, another reaction when you have nitrogen gas plus hydrogen gas to give you ammonia. Ammonia gas. This is a moderate reaction. We can determine the rate of a moderate reaction. The rate of a moderate reaction. We can determine that. Take note of that. Take note, very fast reaction, such as ionic reaction, the rate of chemical reaction cannot be determined. Very slow reaction, such as rusting of iron, you can't determine what? The rate of reaction. You can only determine the rate of a reaction for moderate what? Reaction, which is what? The composition of what? An example of hydrogen peroxide to form this, or reaction between what? Nitrogen gas and what? Hydrogen gas to form ammonia gas. Take note of that. Take note of that. Let's move. Then, how do we measure rate of chemical reaction? How do we measure rate of chemical reaction? Rate of chemical reaction can be measured in two ways. Rate of chemical reaction can be measured in two ways. Rate of chemical reaction can be measured in two ways. The first one is average rate. Average rate of reaction. And the second one is what? Instantaneous. Instantaneous rate of reaction. These are the two ways in which rate of reaction can be measured. The first one is what? Average rate of reaction. The second one is what? Instantaneous rate of reaction. And we are going to look at them one after the what? One after the other. Let's take the first one, average rate of reaction. Average rate of reaction. One love, one heart, let's get together. Feel up, right? Average rate of reaction. Average rate of reaction. Average rate of reaction. Average rate of reaction. This is the change in the concentration of reactant or product over a long period of time. This is the change in concentration of what? Reactant or product over a long period of time. Over a what? Large period of time. That means this is the change in concentration of reactants or products over a long period of time. Over a long period of time. Over a long period of time. For example, when you have, look at this. How can we express average rate of reaction? For example, when you have, let me assume you have x plus y to give z. 3, 2, let me put 4. This. If you were asked to express this in terms of what? Average rate of reaction. Average rate of reaction for this is given as average rate of reaction equal to, don't forget, this is reactant, this is a product. These are what? Reactant, these are product. For product to be formed, the concentration of the reactant will decreases for product to be formed. And as the reactant are reacting, they are decreasing in concentration, while the product is increasing in what? Concentration as it is formed. As the reactant are reacting to form what? The product, the concentration of the reactant will be decreasing, while the product, because the product is being formed from the reaction between X and Y, the concentration of the product increases. That is why for the reactant we use a negative sign. For the product we use what? A positive sign. This indicates that the concentration of the reactant is decreasing to form the product. The concentration of the product is what? Increasing. That is why they say this is the change in concentration of reactant and product over a long period of what? Time. Over a long period of time. Then how do we express this equation in terms of what? Average rate of reaction? This is what? Reactant, which are decreasing in concentration. That means we have minus the concentration of X, which is what? Change in concentration of X over change in time. That means change in concentration over a long period of time. Change in concentration with respect to what? Time. Then don't forget, divide the what? The concentration by what? Stoichiometric coefficient of the reactant. If it is the product, you also divide it by what? The stoichiometric what? Coefficient. What is the stoichiometric coefficient of X? Is what? 3. The stoichiometric coefficient of S is what? 3. Divide this concentration by what? That 3. And it's 1 over 3. Then equal to another reactant, which is Y. That means change in concentration of Y. This thing means what? Concentration. Then concentration of the substance inside, if it is B, that is concentration of what? B. That will be concentration of B. This is concentration of Y. Change in concentration of Y with respect to what? Time. And don't forget, because it's a reactant, a negative sign. A negative sign. Then what is the stoichiometric coefficient of Y? 2. Then divide this by what? 2. That means 1 over 2. Divide the concentration by what? The stoichiometric coefficient, which is true. Then equal to the product, that is positive, increasing, plus change in concentration of what? Z over change in time. Then the stoichiometric coefficient of Z is what? 4. That means divide the concentration by 4. That is 1 over 4. Take note. This is average rate of reaction for this expression. The average rate of reaction for this expression. Let us look at this. Let us look at this. When you have something like this, when you have this, look at this. When you have this, when you have nitrogen gas plus hydrogen gas to give ammonia gas. Put 2 here, put 3 here. Express this in terms of average rate of reaction. Let us look at this. This is a balanced equation. It's a balanced equation. Therefore, the average rate of reaction will be, this is the reactant decreasing in concentration. This is the product increasing in what? Increasing in concentration. Increasing in concentration. The reactant are decreasing in concentration, negative sign. Therefore, for this, we have change in what? Nitrogen gas over change with respect to time, then decreasing in concentration minus, what is the coefficient? The stoichiometric coefficient, 1, that is divided by 1 over 1. Divided by 1. Equal to the second reactant, which is hydrogen gas, negative sign. Then change in what? Concentration of hydrogen gas with respect to what? Time. What is the stoichiometric coefficient? The stoichiometric coefficient of hydrogen gas is 3. Divide it 1 over 3. Divide the concentration by 3, and it's 1 over 3. If like you can write it like this, divided by 3, doesn't mean when you bring it up, it's what? 1 over 3. Equal to the product. The product, that is what? Increasing in concentration, plus you have change in what? Concentration of ammonia with respect to time. What is stoichiometric coefficient? 2. Divide the concentration by 2. 1 over 2. You have this. Take note of this. Take note of this. Try this for me. Try this. Let me give you this. Try this. When you have something like this, try this. When you have this, when you have N2O5 to give NO2 plus O2. Balance equation, put 2 here, put 4, 8, 10. Do this. Pause and do it. Pause and do. Do it, do it. Do it. Do it, do it, do it, do it. Do it, do it, do it, do it. Let's look at it. What is average rate of reaction? The average rate of reaction will be equal to what? Negative sign for reactant, positive sign for product. Why? Increasing in concentration, decreasing in concentration. Therefore, change in what? Concentration of N2O5 with respect to time. Stoichiometric coefficient, that means minus, that means decreasing. Stoichiometric coefficient is 2, that means divide this one by 2. Equal to, we have the product. What is the product? That means we have plus change in concentration of NO2 over change in time. What is the stoichiometric coefficient of NO2? 4. Divide concentration of NO2 by 4. You have this. Equal to, for oxygen, we have plus change in concentration of oxygen gas with respect to time. What is the stoichiometric coefficient? 1. Divide the concentration by what? 1. We have 1 over 1. Take note of that. Take note of that. That is what? Average rate of reaction. Then let us look at what? Average rate of appearance and disappearance. The rate of appearance and what? Disappearance. Don't forget, as you look at the product, at the reactant, as it is decreasing in concentration, that means it is being consumed. As the reactant is decreasing in concentration, it is being what? Consumed. That means it is disappearing. And as the product is being formed, that means the concentration increases. That means it is what? Appearing. Whenever you hear disappearance, it's for the reactant. Appearance is for the product. Disappearance for the reactant because it is decreasing in concentration. It is decreasing in concentration. Negative sign. Decreasing in concentration. That means disappearance. It is being consumed. The product is being formed. That means appearing. That means increasing in concentration. Let us look at how to express. Don't forget, this is average rate of reaction. Let us look at what? Rate of appearance and rate of disappearance. Let me take this one first. Let me take that one first. Let's look at it. Let's move. Because there is a lot of calculation on it. We have a lot from the from what? A-level, Cambridge. We have a lot. Let's look at it. For example, when you have N2 gas plus H2 gas to give ammonia gas. Balance 2, 3. Either what is average rate of nitrogen gas disappearing? Hydrogen gas disappearing. Average rate of what? Appearance of nitrogen gas. Let's look at it. Average rate of appearance or disappearance rather. I'm sorry. Disappearance because it's disappearing. I'm sorry. The reactant is disappearing as it's being formed. It is forming what? The product. It is disappearing. That means concentration what? Decreases. Then as the product is being formed, the concentration what? Increases. That means it's appearing. Product appeared. Reactant what? Disappeared. Product what? Appeared because it's increasing in concentration. Positive. Reactant disappeared. It decreases in concentration. Negative. Then let us look at this. Nitrogen gas. Average rate of disappearance of nitrogen gas is expressed as minus because it is what? Disappearing, decreasing in concentration. Change in concentration of nitrogen gas with respect to what? Time. In this case, take note, when you are looking for what? Rate of disappearance or rate of what? Appearance. Don't use what? Stoichiometric coefficient. Please take note. Don't divide the concentration by what? Stoichiometric what? Coefficient. Don't divide what? The concentration of the species, either the product or the reactant, either the product or the reactant, either the product or the reactant. Don't divide the what? Their concentration by what? Their stoichiometric coefficient. Don't do that. Please. The average rate of disappearance of nitrogen gas is this. Don't divide the concentration by what? The stoichiometric what? Coefficient. Don't do that. Take note. Then equal to, for hydrogen gas, average rate of disappearance for hydrogen gas will be, is a reactant, decreasing in concentration. Change in what? Concentration of what? Hydrogen gas with what? Respect to what? Time. What is stoichiometric coefficient of hydrogen gas? 3. Don't divide the concentration by 3 under what? Average rate of what? Disappearance. Take note. Then let us look at the product. The product is what? Appearing. That would what? Average rate of appearance of hydrogen gas or of ammonia gas. Average rate of appearance because it is being formed. It's increasing in concentration. And product what? Appear. There one will be what? Plus change in concentration of ammonia with what? Respect to what? Time. What is the stoichiometric coefficient? 2. Don't divide the concentration by 2 under rate of appearance, rate of disappearance. Don't. We only divide what? The concentration by what? The stoichiometric coefficient under rate of reaction only. Under rate of reaction only. Not under rate of appearance or rate of what? Disappearance. Take note of that. Please look at this. Do this for me. Do this for me. Do this for me. Hope you understand. Do this for me. Pause the video and do this for me. Do this. Do this for me. When you have N2O5 to give NO2 plus O2, you have 2, 4. Do this. Pause and do. Pause and do this. Pause and do this for me. Pause and do this for me. Oh, direct, yes, they rob I. So that to the mind. Let's look at it. Let's look at this. This is the, find the word, average rate of disappearance of N2O5. For average rate of disappearance of N2O5, we have reactant disappear, the product appears, and concentration of the reactant decreases negative. For average rate of disappearance, that means I have minus change in concentration of N2O5 with respect to what? Time. Then for the product, they are appearing. Therefore, average rate of appearance, the first product, let me take, of NO2 equal to plus change in concentration of NO2 with respect to time. For what? O2. Average rate of appearance of O2 will be equal to what? Plus change in concentration of O2 over change in time. Take note of that. Take note of that. And take note, the average rate of disappearance of appearance, the negative sign doesn't mean. For example, when you have, if average rate of disappearance of N2O5 is minus 2 mole per liter per second, it means that this N2O5 is what decreasing in concentration, is decreasing by 2 moles per liter in every 1 second. Take note. This one means the word, for example, if you have, let me write it properly, if you have average rate of disappearance of N2O5, which is what? According to this, you have minus this O5 over change in theta equal to minus 2 mole per liter per second. It means this reactant, N2O5, is decreasing by 2 mole per liter in every word second. That's the meaning of this negative sign. That the word N2O5, the concentration of N2O5 decreases by what? 2 mole per liter in every word second. That's the meaning. Take note. And take note of this, I should have given you. Rate of reactant. The rate of reaction, rather. Rate of reaction is always positive. Take note. Rate of reaction is always positive. Rate of reaction is always positive. Rate of reaction is always what? Positive. Take note of that. Rate of reaction is always positive. Then let's do some questions. Let's do some questions. Let's do some questions. Let's do some questions. If you have N2, H2 to give ammonia, 2, 3. In the reaction, if the concentration or if 2 moles per liter of hydrogen gas is used or is consumed to produce ammonia in every 1 minute. Find Roman figure 1, rate of reaction. Roman figure 2, rate of appearance of ammonia. Roman figure 3, rate of disappearance of nitrogen gas. Let's do this question. Very simple question. According to this equation, if 2 moles per liter of hydrogen gas is consumed, to produce ammonia in every 1 minute, find rate of reaction. We got to rate of appearance of nitrogen gas is the product. The Roman figure 3, rate of disappearance of nitrogen gas is what? Reactant. Let's do it, please. Let's do it. Let's look at this. Before we find this, express this in terms of what? Rate of reaction, and in terms of what? Average rate of reaction, and in terms of what? Average rate of appearance and disappearance. Let me express this in terms of average rate of reaction. Average rate of reaction, that was the first thing. That's what they want to calculate. Rate of reaction, average rate of reaction. Average rate of reaction, nitrogen, hydrogen, they are reactants. This is a product. For average rate of reaction, I'm sorry, this one is positive. For average rate of reaction for the reactant, that means we are negative. Change in concentration of nitrogen gas with time. What is coefficient? Stoichiometric coefficient, because we are looking for average rate of reaction, not average rate of appearance or disappearance. Average rate of reaction, you will divide the concentration by what? Stoichiometric coefficient, which is 1. That means 1/1. Equal to, for the second reactant minus, we have change in concentration of hydrogen gas with respect to what? Time. That means, what is the stoichiometric coefficient? 3. Divide the concentration by 3, 1/3. Equal to, go to the product, we have positive. Concentration of the ammonia, change in concentration of ammonia with respect to what? Time. Stoichiometric coefficient of ammonia, 2. Divide the concentration by 2, that is 1/2. Divide the concentration by 2, that's the meaning. You have that. Look at this. In the question, they say 2 moles per liter of hydrogen gas is consumed to produce ammonia in every 1 minute. That means this one, hydrogen gas, is being what? Disappeared. Therefore, if you have this, what is average rate of disappearance of hydrogen gas? From what I told you, that means it will be negative. Change in concentration of hydrogen gas with what? Respect to what? Time. This is average rate of what? Disappearance of hydrogen gas. This is what? Average rate of reaction. Average rate of disappearance of appearance. You don't need to divide with what? Stoichiometric coefficient. You don't need the stoichiometric coefficient for average rate of disappearance or appearance. Take note of that. Then they now say 2 moles per liter of hydrogen gas is consumed every what? 1 minute. That means the concentration is given as what? 2 over 1 minute. That means 1 minute make how many seconds? 60 seconds. That means from here, 2 here 1, 2 here what 30. That means I have minus 1/30 mole per liter per second. Take note. Do you understand? This is what the average rate of what disappearance of what hydrogen gas. That means for every 1 second, 1/30 mole per liter of what hydrogen gas is being used to produce ammonia. That's the meaning. For every 1 second, 1/30 mole per liter of hydrogen gas is being used to produce ammonia for every 1 second. That means rate of disappearance of hydrogen gas is what? 1/30. Do you understand? Then the question has said calculate or find what? Rate of reaction. Rate of reaction. Let us look at the rate of reaction. Let me write in here. Is it okay? Therefore, rate of reaction equal to for hydrogen gas. Rate of reaction of hydrogen gas is what? Equal to minus 1/3 change in concentration of what? Hydrogen gas with respect to what? Time. And don't forget, this one only has been given as what? Minus 1/30. Can you see? This one only, without the stoichiometric coefficient, has been given as what? Minus 1/30. That is rate of disappearance of what? Hydrogen gas. That means this is rate of disappearance of hydrogen gas. Then every one of them is what? Rate of reaction. This is rate of disappearance of what? Hydrogen gas. Then everything here is what? Rate of reaction of hydrogen gas. This is rate of disappearance of hydrogen gas. This is rate of reaction of hydrogen gas. And from here now, rate of reaction equal to minus 1/3 times rate of disappearance of hydrogen gas has been calculated as what? Minus 1/30. Minus 1/30. Then from here we have rate of reaction equal to plus, then you have 1/90 mole per liter per second. And I told you, rate of reaction is always what? Positive. It's always what? Positive. Take note of that. This is rate of reaction. Then the second question, they say find rate of appearance of what? Ammonia. Rate of appearance of 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 ammonia. According to that equation, what is rate of appearance? Average rate of appearance of ammonia is equal to plus change in concentration of ammonia with respect to what? Time. I told you that there won't be what? You won't divide the what? The concentration by coefficient or stoichiometric coefficient when you are looking for what? Rate of appearance or rate of disappearance. This is rate of appearance of ammonia. Then they now ask you to calculate your rate of appearance of ammonia. Then go back to the average rate of reaction. What is average rate of reaction of ammonia? Is it? We have average rate of reaction of average rate of reaction for ammonia is what? Plus 1/2 change in what? Concentration of ammonia with respect to what? Time. But they want you to find this only, which is what? Average rate of appearance of ammonia, this only. And don't forget, what is rate of reaction? Average rate of reaction. Average rate of reaction is what? 1/90. That means I will now write average rate of reaction is what? 1/90 equal to plus 1/2 change in concentration of ammonia over change with respect to time. Then this one come here, we have what we have? 2/90 equal to what? Change in concentration of what? Ammonia over with respect to what? Time. Therefore, this one will be 1/45 mole per liter per second. That is average rate of appearance of what? Ammonia. Average rate of appearance of ammonia is 1/45. The next one, find what? Rate of disappearance of nitrogen gas. I believe you can do that. Rate of disappearance of nitrogen gas. Don't forget, rate of reaction is what? 1/90. Therefore, rate of disappearance, that means for rate of reaction, we have 1/1 minus 1/1 over this. They want you to look for what? Calculate only this one. Only this one. What will happen? This one will come here. You have what? What we have? We have 1/90. The answer will be what? 1/90 mole per liter per second. I told you the minus doesn't mean you can leave the minus, the negative sign does not mean anything. Does not mean anything. Does not mean anything. It's absolute value, doesn't mean anything. Take note. Let's move further. Let us go to instantaneous. Instantaneous rate of reaction. Instantaneous rate of reaction. Instantaneous rate of reaction. Instantaneous rate of reaction. What is instantaneous rate of reaction? Instantaneous rate of reaction. Instantaneous rate of reaction. This is when we consider average rate of reaction. When you consider average rate of reaction at the smallest time interval. When you consider what? Average rate of reaction at what? Smallest time interval, in which what? Change in time is approaching what? Approaching zero, tending toward zero. This is when average rate of reaction is considered at the smallest time interval. At the smallest time what? Interval, in which change in time is tending, approaching what? Zero. Approaching zero. Take note of that. That means the rate of reaction at a particular instant of time. The rate of reaction at a particular instant of time. The rate of a reaction at a particular instant of time. When you consider average rate of reaction at the smallest time interval, in which what? Change in what? Time is tending toward zero. That means this instantaneous rate of reaction measure rate of reaction more accurate than what? Average rate of reaction. Take note of that. Instantaneous rate of reaction measures rate of reaction more accurately than what? Than average rate of reaction. I repeat, instantaneous rate of reaction measures accurately rate of what? Reaction more than what? Average rate of reaction. That means this one measure more accurately rate of reaction than what? Average rate of reaction. Take note of that. Then what is the relationship between average rate of reaction and instantaneous rate of reaction? It's in your exam. We have instantaneous rate of reaction is equal to when you have change in time tending toward zero, approaching zero, then average rate of what? Reaction. Take note. This is an expression that shows the relationship between instantaneous rate of reaction and what? Average rate of reaction. Take note of this. Take note of this. The rate of a reaction at a particular instant of time. The time is not what? Zero yet, but it's approaching what? Zero. Take note. when you consider what average rate of reaction at the what smallest, at the smallest time interval. That is what instantaneous rate of reaction. Instantaneous rate of reaction. And for instantaneous rate of reaction, we use what? D concentration. D concentration. D concentration. We don't use the data. We use what? D. That means, let's look at it. Let's move. Let's move. When you have this, what is the graphical representation of instantaneous? For example, when you have x plus y equal to what? Z. X plus y equals to z. Don't forget the graphical representation of instantaneous rate of reaction. Instantaneous rate of reaction. Instantaneous. The reactant decreasing in what? Concentration. The product increasing in what? Concentration. The graphical representation for the what? First reactant, when you have concentration of what? X mole per liter. Respect to what? Time. Seconds. Is a what? A decreasing what? Graph. A decreasing graph. A decreasing graph. Then for Y, when you have, for Y, the same, you have concentration of Y, mole per liter, then time here, S axis, seconds, then decreasing graph. For Z, which is increasing concentration, the product, for product, this is what? These two, this is a reactant. This is also what? Reactant. For the product is increasing in concentration. What was the product? Z. Concentration of Z, which is giving you what? Mole per liter. Then time is what? Seconds. It's increasing in concentration. You have something like this. It's increasing in concentration. Then what is the slope? This at this point, instant of time. The slope, you can have the slope like this. That means, which is for tan theta. For here, you can have slope, tan theta. For this one, you will extend them at this particular point in time. Okay, let me take note of this. The slope. Then what is the slope? We have slope for this. Before for this, and we have dx dt equal to slope equal to what? Tan theta. For this one, and we have the concentration dt equal to what? Slope tan theta. The same thing, but before let me explain this before we move to this. Look at this. Look at this. When you have, let me assume you have x plus y equal to z. Let me put here. Instantaneous rate of a reaction. If they ask you to express this in instantaneous now, instantaneous rate of reaction. Instantaneous rate of reaction equal to, this is the reactant, decreasing, product increasing, rate of reaction, not rate of appearance or disappearance. For rate of reaction, we need the word stoichiometric coefficient. Let me put 3 here, let me put 2 here. For the word rate of reaction, we need stoichiometric coefficient. It's only for the word rate of appearance or disappearance that we don't need the word stoichiometric coefficient. For this one, instantaneous rate of reaction, for this is negative side, decreasing in concentration. Therefore, dx over dt. What is the stoichiometric coefficient for S? 2. That is, divide the concentration by 2. 1 over 2. Equal to instantaneous rate of reaction for this. We have negative sign, dy, dt. Divide the concentration by the stoichiometric coefficient, 1 over 3. That means divide this concentration by 3, and it's 1 over 3. Equal to, for this, plus the T, divide the concentration by what stoichiometric coefficient, 1 over 2. This is expression for instantaneous rate of reaction. Instantaneous rate of reaction. Then for instantaneous rate of appearance and disappearance, just remove the word stoichiometric coefficient. For instantaneous rate of appearance and disappearance, just remove the word stoichiometric coefficient. Let us look at that. Let me look at that. Like, okay, let me I'll still re-explain this. Let me look at that. Let me look at that. For instantaneous rate of disappearance of X, instantaneous rate of disappearance of X, what will I write? Negative sign, then dx, the t. I don't need the stoichiometric coefficient. For instantaneous rate of disappearance of y, the same thing. That means negative is decreasing, is disappearing, minus dy, the t. I don't need the stoichiometric coefficient. For instantaneous rate of appearance of z plus dz dt. Take note. Take note. Take note. Take note of that. That's that. Take note of that. That's that. For instantaneous rate of disappearance, or average rate of disappearance, or average rate of appearance, or instantaneous rate of appearance, we do need the word stoichiometric coefficient. Take note. Take note. Then let's move further. Let's move further. Because we have more questions from the Japan, from here, which we are going to solve. Then I said, when you have x plus y to give you z, for example, for this, the graphical representation for this, we have, because it's decreasing in concentration, that means we have time, which is given in seconds. In seconds, we have a concentration of x, which is given in mole per liter, then decreasing. Take note. Then what will be the slope? The slope at a very instant, a particular instant of time. Here, the slope, we have tan theta. Then what is slope? You know that this is what disappearing is disappearing x. That means the instant rate of disappearance. Express this instant rate of disappearance. Instant rate, let me put 3, 2, 2. Instant rate of disappearance of x. Instant rate of disappearance of x. Equal to, because it's decreasing in concentration, minus dx dt. Don't forget, I don't need the word coefficient, stoichiometric coefficient for rate of disappearance or appearance. I won't divide the concentration with what stoichiometric word coefficient for this. Then equal to the slope, which is also tan theta. The slope for this. Then for y, the same graph. For y, when you have this, we have concentration of y in mole per liter. Then we have time, seconds, then decreasing in concentration. Then you have at instant of time, you have this one, a tangent line that intersect your y-axis and the x-axis. You have then the slope or the rate of disappearance for this. We have minus d rate of disappearance, instantaneous rate of disappearance, instantaneous rate of disappearance. For this, you have minus dy dt equal to, which is the slope, equal to what? Tan theta. Take note of that, tan theta. Then for the product, because it's increasing in concentration, the product is increasing in concentration. We have concentration of Z given in mole per liter, then time given in what? Seconds. We have this. Then let us take the what? At instant of time, the slope. Extend this. We have something like this, the slope tan theta. Then for this one, instantaneous rate of appearance. Instantaneous rate of appearance of Z equal to what? dZ, concentration of dt equal to is positive plus is positive equal to the slope, which is equal to what? Tan theta. Take note. This is graphical representation of instantaneous rate of reaction. Take note of that. Take note of. Okay. Let's look at some numerical questions. Let's look at some questions, please. We have to be fast because of time. Look at this question. If you have question 1, nitrogen gas plus hydrogen gas to give ammonia gas. Balance question 2, 3. You have the graph of instantaneous rate of disappearance of hydrogen gas. Rate of disappearance of hydrogen gas. Mole per liter. The time, seconds. We have 12. We have 2. When concentration is 8, time is what? 4 seconds. Find Roman figure 1, ROR, rate of reaction. Roman figure 2, find what? Rate of appearance of ammonia. Let's look at this. This is what? Graphical representation of instantaneous rate of disappearance of hydrogen gas. Hydrogen gas is being consumed to produce ammonia. The rate of disappearance is given like this. That means dropping graph, decreasing. That means dropping graph. Then, what is slow? Before we move, find what? Express this in terms of what? Instantaneous rate of reaction. Instantaneous rate of reaction. Express this in terms of instantaneous rate of reaction so that you can understand better. Instantaneous rate of reaction. For this, we have minus dN to dt equal to divided by 1 because rate of reaction. For hydrogen, minus 1/3 instantaneous rate of reaction. dH2 dt equal to, for this, increasing, positive. The ammonia, is it okay? dt divided by stoichiometry 1/2. Is it okay? Then from here, now let us go back to this. Look at this. What is what? Now, hydrogen gas is being consumed, disappearing. That is instantaneous rate of what? Disappearance of hydrogen gas. Instantaneous rate of disappearance of hydrogen gas is given minus dH to dt. You don't need coefficient, stoichiometric coefficient under what? Disappearance or appearance. I've told you that. Then from there, which is the same thing as for slow, which is the same thing as for tan theta. And what is slow? We have slow equal to what? Change in what? Y axis over what? Change in what? X axis. What is the final concentration? 8. Final concentration is 8. 8 minus initial concentration, because it's dropping. It's a dropping graph, decreasing graph, negative graph. The initial concentration is what? 8. Final is what? Oh, initial concentration is 12. Final is what? 8. Initial concentration 12. Final concentration 8. And final concentration y2 minus y1 over s2 minus s1. Don't forget that. Slow is given as what? Change in y-axis y2 minus y1 over s2 minus s1. Final minus initial. Final minus what? Initial. That means the initial is 12. For time, the final 4 minus what? Initial 2. Therefore, the slope is what? Minus 4 over 2. 2 here 1, 2 here 2. You have slope equal to what? Minus 2 mole per liter per what? Second. And don't forget, I told you, rate of disappearance of hydrogen gas is the same thing as what? The slope. Therefore, minus the H2 dt is what? Minus 2 mole per liter per second. Which means concentration of hydrogen gas is decreasing or disappearing by 2 mole per liter in every 1 second. That means its concentration of hydrogen gas is decreasing by what? 2 mole per liter for every 1 second to form ammonia. That's the meaning. Decreasing minus decreasing is decreasing by what? 2 mole per liter for every 1 second to form what? Ammonia. Then from there, the next question says find rate of reaction. Rate of reaction. And I know what is rate of reaction in terms of what? Hydrogen gas. I have instantaneous rate of reaction. In terms of hydrogen gas is what? Minus 1 over 3. The hydrogen gas dt. And don't forget, this one rate of disappearance of hydrogen gas is what? Minus 2. Just change it. This is minus 2. Just change it. You have instantaneous rate of reaction equal to minus 1 over 3 times minus 2, which is instantaneous rate of reaction equal to minus, then you have 2 over 3 mole per liter per second. That is instantaneous rate of reaction. Take note of that. Then the next question, it says calculate rate of appearance of ammonia. Rate of appearance of ammonia. Please let me rub off this one. I hope you've written down the question. Pause and write down the question. Rate of appearance of ammonia from the instantaneous rate of reaction. Instantaneous rate of reaction in terms of ammonia is what? Plus 1 over 2. The ammonia, the what? T. Don't forget this one. That's what they want you to calculate. Rate of what? Appearance. Appearance. I told you it won't need what? Stoichiometric coefficient. This is what they want you to calculate. Rate of appearance of ammonia. Rate of appearance of ammonia. You know that rate of appearance of ammonia. Rate of appearance of ammonia. From that reaction, you can have it as plus the ammonia, the what? T. That's, they want you to calculate rate of appearance of ammonia, only this one. Then from here, you have what is rate of instantaneous rate of reaction? It's what? 2 over 3. This one is given as calculated as 2 over 3 equal to 1 over 2. Then you want you to calculate this. I'm sorry, this is 3 dt. What happened? This one going here, we have 2 times 2 over 3, which is what? The rate of appearance of ammonia. That means, which is what? 4 over 3. 4 over 3. mole per liter per second. Take note of that. That is rate of appearance of what? Ammonia. Take note of that. Let's move to another question. Another question. Another question. Another question. Please pause. Go through it. Pause. Go through it. Please don't forget to what? Subscribe. Don't forget to subscribe. Press the subscribe button. Share and like with your friend. The JUPEP student, the IJMB, the A-level student, share together with what 100-level student, share, and you can buy course from us. Call one of those numbers you see on the screen. If you are ready, you are going to anywhere you are, writing JUPEP, writing what IJMB, Cambridge A-level, call one of those numbers. Physics, chemistry, math. Physics, chemistry, math will be taken care of. Your A is certain. Your A is what? Certain. Press the subscribe button, share, like, comment. If there's anything you want, comment. Then call one of those numbers. Please, thank you. Let's move. Another question. Another question. Another question. Another question. When you have 2w plus x equal to y. 2w plus x equal to what? Y. Then you have this. You have 45. You have concentration of W in mole per liter. You have time in seconds. Find rate of reaction. That's first one. Second one, find rate of appearance of Y. Rate of appearance of Y. Find rate of appearance of Y. Don't forget, if you don't know how to solve it, just be calm. First of all, write instantaneous rate of reaction for this. Just write, let me hear solution. Don't rush, just be calm. For this is negative, positive. Instantaneous rate of reaction. Now, instantaneous rate of reaction equal to, for this, you have -1/2 dW dt equal to -1/1 dx dt equal to plus, this one is plus 1/3 dy d what? dt. That is rate of reaction. Rate of reaction. Then look at this. Is it? W is a reactant. That means this is instantaneous rate of disappearance. Instantaneous rate of what? Disappearance. Then the rate of disappearance of W. Rate of disappearance of W. That means instantaneous rate of disappearance for W will be equal to minus dW dt. I don't need the stoichiometric coefficient for disappearance or appearance. Then from here, I know that rate of disappearance, which is instantaneous rate of disappearance of W equal to minus dW dt equal to slope equal to what? Tan theta. We know that, tan theta. The angle is given here. Which angle are we going to consider? The one in the direction of positive x-axis. We consider the one in the direction of our positive x-axis, which is what? 180 minus 45. And 180 minus 45 is what? 135. This one is not this. The one in direction of what? X, positive x-axis. The one in direction of positive x-axis. And it's 180 minus 45, which should be what? 135 degrees. This one. Therefore, we have minus dW dt equal to what? Tan theta, which is what? 135. Therefore, minus dW dt equal to 35 is what? Minus 1. Minus 1. That is rate of what? Disappearance of what? W. Then, if you want to calculate rate of reaction now, instantaneous rate of reaction. Let's move. Instantaneous rate of reaction. Instantaneous rate of reaction. Instantaneous rate of reaction. That means instantaneous rate of reaction. Rate of reaction. With what? W. Minus 1 over 2. The W. The T. Rate of disappearance of what? W. Reactant W has been what? Calculated as what? Minus 1. Just changes. I want you to calculate instantaneous rate of reaction. Instantaneous rate of reaction will be equal to minus 1 over 2. This one, rate of disappearance of W is what? Minus 1 times minus 1. Therefore, instantaneous rate of reaction equal to, we give you half. I told you, rate of reaction is always what? Positive. Either average rate of reaction or instantaneous rate of reaction is always what? Positive. Take note. Then the second one, rate of appearance of Y. Rate of appearance of Y. They say calculate rate of appearance of Y. Rate of appearance of Y. Let us relate instantaneous rate of reaction and what? To Y. We have instantaneous rate of reaction equal to what? Plus 1 over 3 dy dt. The question says calculate rate of appearance. This is just the rate of appearance without the stoichiometric coefficient. This is rate of appearance without the stoichiometric coefficient. And instantaneous rate of reaction is what? Minus what? 1. Minus 1. Yeah, it's minus 1. Then equal to this one, 1 over 3. Change dy dt. They want you to find the rate of appearance. This one come here. Yeah. Instantaneous rate of reaction equal to, what is instantaneous rate of reaction? Is half. I'm sorry, is half. Instantaneous rate of reaction, because I'm fast because of time, instantaneous rate of reaction is what? Half. That is 1 over 2 equal to 1 over 3 dy dt. Then for you to calculate instantaneous rate of appearance of Y, this one, this is rate of appearance of Y. Rate of appearance of Y. This one coming, you have 1 over 2 times 3 equal to what? Rate of appearance of Y. Therefore, rate of appearance of Y is what? 3 over 2 mole per liter per second. That means rate of appearance of Y. Let us look at this last question in Juppé. This last question in Juppé. Last question from Juppé. Last question from Juppé. Last question from Juppé. Because I have 3 minutes left. Last question from Juppé. Then I will give you one assignment, which we have this. The rate of formation, the rate of formation of oxygen gas is 2.0 times 10 raised to the power minus 7 mole per liter per second. For the reaction, 3 moles of oxygen to give 2 moles of ozone. What is the rate of disappearance of, this one is O3. Okay, we have this. The rate of formation of O3 ozone is for the reaction below. What is the rate of disappearance. What is the rate of disappearance of O2, of oxygen gas? Oxygen gas in mole per liter per second. Option A, we have 1.3 times 10 raised to the power minus 7. Option B, we have 2.0 times 10 raised to the power minus 7. Option C, we have 3.0 times 10 raised to the power minus 7. Option D, we have 4.5 times 10 raised to the power minus 7. Please let us solve this question. They want you to calculate what? Rate of disappearance of O2 according to this. This is O2, is the reactant, is the one that disappears. This is what? Ozone is the one that is formed, appearance, formation. Therefore, instantaneous, first of all, right, instantaneous rate of reaction. That means we have, this is minus plus. Instantaneous rate of reaction, we have minus 1 over 3 dO2 dt equal to, for the product, plus 1 over 2 dO3 dt. Then rate of formation of this, rate of appearance of this, rate instantaneous rate of appearance of O3 will be, we have plus dO3 dt. For rate of appearance, we don't need what? The stoichiometric coefficient. That is very simple. And I say the rate of formation of O3 is given like this, is given as 2.0 times 10 raised to the power minus 7. That means rate of formation, rate of appearance of O3 is given as 2 times 10 raised to the power minus 7 mole per liter per second. From there, we can get what? Rate of reaction. Rate of reaction, that means instantaneous rate of reaction, equal to, for O3, we have plus 1 over 3 dO, is it 1 over 3? 1 over 2 r, plus 1 over 2 dO3 dt. Then instantaneous rate of reaction equal to plus 1 over 2. This rate of appearance of O3, rate of formation, which is appearance. Formation means what? Appearance. Consume means disappearance. Used means disappearance. That is reactant. Formation means what? Appearance. That is product. This one, rate of appearance of this product, is given as this. That means times 2 times 10 raised to the power minus 7. 2 here cancel. We have instantaneous rate of reaction equal to 1 times 10 raised to the power minus 7 mole per liter per second. But the question says calculate rate of disappearance of O2. Therefore, rate of disappearance of O2, rate of disappearance of O2 will be equal to, from here, will be equal to rate of disappearance of O2 is what? dO2 dt. That is rate of disappearance of O2. But look at instantaneous rate of reaction in terms of O2. Instantaneous rate of reaction in terms of O2 is given as minus 1 over 3. That means dO2 dt. But they want you to calculate this only. That's what they want you to calculate. This only. This only. And instantaneous rate of reaction has been calculated as 1 times 10 raised to the power minus 7. Let me come here. You have instantaneous rate of reaction is 1 times 10 raised to the power minus 7 equal to minus 1 over 3 dO2 dt. They want you to find this one only. That is rate of disappearance of oxygen gas. This one only. What about this one? Come here. 3 times 1 times 10 raised to the power minus 7 equal to minus dO2 dt. Therefore, this one will give you what? 3 times 10 raised to the power minus 7 minus dO2 dt. That means the option is what? C. The option is C. Let me give you an assignment to solve. It's a JUPEP question assignment. Take this assignment, please. Take this assignment. Put your answer in the comment below. This is the assignment. We have the assignment. The instantaneous let me rub everything off. The instantaneous rate of disappearance of the instantaneous rate of disappearance of NN04 minus is 4.56 times 10 raised to the power minus 3 mole per liter per second. According to the reaction below, 2 Mn04 plus 10 plus 16 hydrogen ion to give 2 Mn, 2 plus 5 moles of hydrogen plus 8 moles of water. The rate of appearance of iodine vapor is option A. We have 1.14 times 10 raised to the power minus 3. Option B, 5.7 times 10 raised to the power minus 3. Option C, we have 4.56 times 10 raised to the power minus 4. Option D, we have 1.14 times 10 raised to the power minus 2. We have this. Please take it as an assignment. Please drop your answer in the comment section. And if you want the answer to this, the explanation, you can call one of those two numbers on your screen. If you need an explanation to this, then subscribe to our channel, like, comment, and share with your friend. JUPEB student, IJMB, A-Level Cambridge. Please, thank you.